We will then do 1 or 2 lectures on final exam review. And then, my gosh, it'll be exam week. So isn't this all exciting? It is.
On what days are final?
I don't know. But I will find out.
Okay.
Is it gonna be like here in class or will it be like in the testing center?
All right, today we're going to do chapter 11. Like I said, this is alkyl halides. We talked about alkyl halides in chapter 10, but we did that within the context of free radicals, and we actually only did one real reaction of alkyl halides. Now, it's a very, very important reaction, and like I said, I assure you, it will be on the exam, and that is the Grignard reaction. Make sure you understand how to do that. Make a Grignard reagent, basically reacting with a carbonyl to get an alcohol. Fairly simple reaction, but still very, very important. You'll spend, a whole lot of time in chapter 17 going over that. Well, today we're going to talk about alkyl halides again, and we're going to instead focus on other common reactions, and these are basically substitution and elimination reactions. And we've talked about substitution throughout the semester, really, so nothing here is particularly new. Eliminations are kind of something we haven't talked about yet. Let's go back to old general chemistry somewhere and just review what we know about polar covalent bonds. Because polar covalent bonds are very important in organic chemistry. They're the kind of things that make all of this stuff work. This is bromomethane. Remember, in electrostatic potential map, we use color to map effectively electron density, not exactly, but close. In bromomethane, the bromine is much more electronegative, draws the electrons away from the carbon towards itself. We wind up with the negative end of the molecule, and the carbon is positive. Now, this is important because this means that this carbon is what's known as an electrophile. That is, it wants electrons because it's positive. Chloride anion would be an example of a nucleophile. Nucleophile is something that has electrons and would love to find something positive to share them with. This is chloromethane, not bromomethane. But when you have an electrophile and a nucleophile together, basically what happens is the electrons from the nucleophile will attack the positive center. When this happens, go ahead and get my arrow, there it is. It will attack the positive center. This bond will then break, and we will make a new compound. This is a very simple substitution reaction. The whole thing would look something like this. Chloride as our nucleophile, chloromethane here as our electrophile. This is the electrophilic center here. Chloride attacks. As it does, the bond here to the other chlorine breaks, and we wind up with chloromethane and another mole of chloride anion. This is, as we've said before, what's known as an SN2 reaction. S stands for substitution, N for nucleophilic, and 2 for bimolecular. Now, we'll talk a little bit about what we mean by bimolecular. Basically, all it means is that in the rate-limiting transition state, we have 2 molecules. So we'll see that in just a moment. In a very simple analogous reaction here, we're going to make an ether. we're going to make this ether using something like bromomethane and methoxide. This is actually known as the Williamson ether synthesis. Now, very, very simple reaction. It's amazing that he got his name on it, but he did. Everyone knows it as the Williamson ether synthesis. Here, methoxide is our nucleophile. Remember, things with electrons are going to be our nucleophile. This is our leaving group here. That's what's going to leave, is going to be the bromine. The way this happens is the nucleophile will attack the electrophilic center, and the bromine as a leaving group will simply depart. We do this with little curvy arrows. Attack, it's gone, and we wind up with the ether here. This is methyl ethyl ether and bromide anion. 2-methoxyethane is the proper name. In this reaction, in the rate-limiting transition state, we have both the nucleophile and the electrophile. They're both in there. Now, the rate of a reaction, the rate at which it happens, is going to be proportional to the number of molecules, the number of transition states that you can come up with. If you have more transition states, you're much more likely to have a reaction and to make a product. If you have more of either of these, forming the transition state is more likely. Therefore, the rate is proportional to both this guy and to this guy. That's what we mean by simple second order. In physical chemistry, we will talk a lot about kinetics. But this is just a very simple second order reaction. Again, both of these are in the rate-limiting transition state, and that's why this is bimolecular. If we wanted to really think about this reaction, there are two possible mechanisms that we could write for it. Now, we've shown a mechanism on the other slide, but that's not necessarily the proper mechanism. We could also do this using a front-side displacement mechanism. Here's our nucleophile. It's the electrophilic center. In our front-side displacement, we would simply say that the nucleophile attacks, this leaves, and we have a transition state that looks like this. Again, this is a bimolecular transition state because the nucleophile and the electrophile are both in the activated complex. This would give us this product, and again, bromide anion. Now, the mechanism that we've drawn up to now is slightly different. It's a backside displacement. In a backside displacement, the nucleophile is going to attack here on the opposite side of our leaving group. This is what the transition state looks like, and this is what we get for products. Again, a second order transition state. We have the nucleophile and the electrophile both in there. Now, these days, we can do fairly sophisticated computer simulations. Now, what we're going to look at are some simulations for both of these transition states. And we're going to try to rationalize which one would be more likely. Let's start with the front side. This is what we set up on our computer. We have our electrophilic center here. Here we have a bromine coming in and a bromine coming out. Again, both on the same side. We can calculate charges for this transition state. When we do this, we get about minus 0.23 for each of the bromines. And this carbon actually winds up with a negative charge. Now, that's odd, but this is the way the calculations come. You see the carbon here is this little green belt, and it's actually fairly negative. That's unusual. So remember these, minus 0.23 and a negative carbon. If we go to the backside displacement, we have bromine coming in, there's the electrophile, bromine going out. Calculate charges. We're about minus 0.7 for each of the nucleophile and the leaving group, and now we have a nice positive carbon. This is much more fitting. Again, you can see the electrostatic potential map. Here's our carbon buried here in the middle. The electron distribution here is just much more logical, based on electronegativities and everything else. So our best guess here would be that this substitution is going to follow a nice backside displacement. But we can prove this because the one thing that's unique about the backside mechanism is that it leads to inversion of stereochemistry or stereochemical configuration. If we look at this guy, this is a chiral center, isn't it? We're going to attack this with chloride. Bromine is going to leave. In our product, we're going to now have a chlorine bonded, a methyl, an ethyl, and a hydrogen. So we're starting with a chiral center here, and we're going to wind up with a chiral center, if it is truly a backside displacement. Our configuration here, bromine is the highest priority. The ethyl group would be next, methyl, hydrogen is the lowest, and it's in the back. This is an R configuration. When we do this reaction on pure R2-bromo-butane, this is the product that we get. Now, once again, our highest priority is going to be the chlorine, followed by the ethyl, followed by the methyl. This is now S configuration. We know that this reaction, the substitution SN2 reaction, proceeds with a backside attack simply because when we do this, we wind up with inversion of configuration. Started with R, wind up with S. Very important point to understand.
Does it always attack from like the opposite side?
Always attacks directly opposite your leaving group. Make sure that you understand this because this is a very important concept. We can rationalize why one transition state is better than the other, and we'll look at those again, but this is really the picker. We do inversion of configuration. It must be backside. If you think about the two mechanisms that we talked about, here we have a planar carbon in the middle. That's why we get inversion. But here, since one comes in as the other leaves, this would give retention of configuration. Therefore, the conclusion is SN2 reactions, simple backside displacement. Now, all the way back in chapter 6, we talked about this and actually presented this movie where we show very clearly that we have this nice backside displacement. You'll note the configuration here, our central carbon just flips as we go and make bonds from one to the other. Again, if we started off with R, at this point we would now have S. Any questions? Very nice little movie, actually. This point in the middle here, where this carbon is planar, that's our transition state. And once again, the transition state looks something like this. Planar, nucleophile, leaving group, the electrophilic center's in the middle, and it is bimolecular, one more time, because both the nucleophile and the electrophile are present in the transition state together. There's no intermediate here, there's simply a transition state. Any questions? Let's see, I think I'm going to skip that one. So this is what we know about a simple SN2 reaction. In a simple SN2 reaction, the rate is proportional to the concentration of both reactants. That's because they're both present in the transition state. Reaction proceeds with inversion of stereochemistry. That's very important. We will, on this exam, have questions where you need to demonstrate the inversion of the stereochemistry. So make sure you review that. And third, the reaction is deemed concerted. When we say the word concerted, what that means is simply that we do not have an intermediate. We only have a transition state, and everything happens all at once. Any questions? Now, a substitution reaction is actually very, very simple. All you're going to do is identify your nucleophile, identify the electrophilic center, and you're going to substitute. Your leaving group is going to leave, nucleophile comes in. If you have a chiral center, you have to show it being inverted. Let's just go ahead and look at some very simple examples here. This is a generic alkyl halide. This is shown as a primary. And when we're dealing with SN2 reactions, we really want to focus on primary and sometimes secondary products. Go ahead and very quickly just write down the products of these very generic reactions. Here in our first reaction, our nucleophile is going to be hydroxide anion. The oxygen has the electrons. It is the nucleophilic center. This is our electrophile, and of course bromine is the leaving group. Oxygen will attack, bromine will leave, and we just made an alcohol. In our next one here, instead of using OH, I'm using an alkoxide. So we saw this with the Williamson ether synthesis, didn't we? This would be something like methoxide. Once again, the electrophilic nucleophilic center here is going to be the oxygen. Bromine is going to leave, and all we do is make the ether. Oops.
So is bromine the leaving group in every scenario?
Your leaving group will always leave. The leaving group can vary. Right now, we're still talking about alkyl halides. So we're going to do iodide, bromide.
But in this case, for all four of these,
Yeah.
bromine will
Bromine will leave.
Okay.
Our next one, we're using a generic representation of a halogen. Again, halogen attacks, halogen leaves, make a different alkyl halide. This is the carboxylate anion, isn't it? Remember, we have a carbonyl. This is an O-. This is simply going to attack. Again, the bromine leaves, and we make a carboxylate ester. Any questions? Well, we actually talked about substitution reactions back in chapter 9 as well. Let's just review what we said here. Remember, we said that we could take an alkyne and convert that to an alkyne anion by reaction with sodium amide. The NH2 minus is our base here. Not a nucleophile, it's a base. What we're doing is simply removing the hydrogen from the end of the alkyne, and we're making the alkyne anion. So what we're going to do is use this then as a nucleophile in an SN2 reaction. Again, we did this in chapter 9. Here we have iodomethane, and I've simply shown attack of the nucleophilic carbon here on this. Iodide leaves, and we wound up with an alkylated alkyne. So we've talked about this. There's one other nucleophile that we want to address here very simply, and that is nitrogen nucleophiles. If a nitrogen attacks, well, in this case we would make an alkyl azide, but here we're going to make amines. So very quickly look at this list and predict the products that we would get from these reactions. For an SN2 reaction, it really is just very, very simple. Nucleophile is going to attack the electrophilic carbon, and the leaving group will leave. Azide, we have a terminal nitrogen with a negative charge. That will simply attack, and will make the alkyl azide. Alkyl azides are notoriously explosive compounds because 2 of the 3 nitrogens would just dearly love to be elemental nitrogen. So the things are very unstable, break down, and go boom. Now the next reaction, we have a simple amine here. This is ammonia. Again, the nitrogen has a lone pair of electrons. It's going to be our nucleophile. Bromine is still our leaving group. And we wind up with a bond here between the nitrogen and the electrophilic carbon. Now, initially, the product is going to look like this. That's because we have 4 things bonded to our nitrogen now, don't we? Remember, ammonium in H4, 4 things on nitrogen, it's positive. So initially, we would form the ammonium ion. In reality, this will undergo equilibrium ionization and give you the free amine. Instead of using a simple reaction with ammonia, this is dimethylamine. Now, dimethylamine, same thing. Nitrogen still has a lone pair of electrons, still attacks. In this case, we would get the tertiary amine as our product. Again, I've shown this as the ammonium because that's what's formed first. But on an exam or something, if you wrote this without the hydrogen or the positive charge, that would be acceptable. Nitrogen, 2 methyls, and now the alkyl group attached. Here we have trimethylamine. Trimethylamine is a compound with an unpleasant odor, very low boiling point. It's the odor of bad fish. Okay? Trimethylamine, nitrogen again is our nucleophile, bromine the leaving group. Here we make the quaternary ammonium salt. Now this must always wind up with a positive charge because there's no hydrogen to lose. So, simple SN2 reaction. Identify your nucleophile. Identify the leaving group. And you simply substitute the two of them. Very, very simple. If you have a chiral center, remember you must invert the configuration. All right. Now, I said that we were talking about primary and sometimes secondary centers, right? I said that. That's because if we use a tertiary center, things are typically different. The rate of the reaction. Remember we said it was bimolecular with a primary alkyl halide. Here the rate of the reaction is unimolecular. Concentration of the nucleophile doesn't have any effect on the rate. So the only thing in the transition state is going to be the alkyl halide. This is a first order reaction. Remember with a primary alkyl halide, we had retention of stereochemistry. Here we don't. Here we have racemization. Racemization means that if we started off with R, we would wind up with an equal mixture of R and S. A racemic mixture, both enantiomers, equal quantities. Finally, with primary alkyl halides, an SN2 reaction is just as clean and nice as you could want. It just happens. You take one off, put the other one on. With a tertiary, we get rearrangements. Now, whenever you see a rearrangement, you should immediately think carbocations, right? Because we know carbocations can undergo rearrangement. We'll talk a little bit about that. Clearly, this is a different mechanism. This is going to be our SN1 reaction. This is an example of the racemization. Here I have a tertiary alkyl halide. This is the R enantiomer of 3-bromo-3-methylhexane. And I'm doing a simple reaction here, I hoped, with methoxide. If this was a simple SN2, this would come in, bromine would leave, and we would have the S isomer. In fact, we wind up with the S enantiomer and the R enantiomer in equal quantities. Equal quantities. So again, something different is happening here. The thing that's different, that's happening, is we are taking our compound and instead of bringing our nucleophile into the same transition state, this thing is doing something all by itself. Now the fact that we get rearrangement strongly suggests that what we have is a first step to form a carbocation. Once we have the carbocation, remember it's planar. Because it's planar, we could bring our nucleophile in now, either from the top or the bottom, and that's why we would get a racemic mixture. The top would give one enantiomer, the bottom would give the other. So it looks something like this. Methoxide can come in the top this way, and that would give us the S enantiomer. If it comes in from the bottom, we get the R enantiomer. So the stereochemistry again strongly suggests that we have carbocation intermediate, and once again we have racemization of stereochemistry. This reaction is also unimolecular. Remember, carbocations form spontaneously, but slowly. The slow step in this reaction is the ionization of this thing to form the carbocation. Once we have the carbocation, it's very reactive, isn't it? So the nucleophile is going to add the very first chance in a fast step. This is unimolecular because the only thing in the rate-limiting transition state is the electrophilic center. The addition of methoxide to it is going to be a very fast step. This is our rate-limiting step, and this one is fast. So that's why this is unimolecular instead of bimolecular. We can show this using, again, this is called SN1, substitution, nucleophilic, just like before, except one means unimolecular. Now remember, we did reaction coordinates. For a carbocation forming reaction, we would have something like this. Here's our tertiary alkyl halide. Slow step is loss of the halogen to form the carbocation. This is what the transition state looks like, and that's right here. Then we form the carbocation itself. The fast step, remember the distance here is proportional to the rate. So the fast step is now addition of this to this, that's this guy, and boom, you have products. Only thing in the rate-limiting transition state is the electrophilic carbon. Now this all makes great sense, but it always looks nicer if you do it in a movie. Here we have tert butyl chloride. In fact, this is very similar to a reaction that we did in lab, isn't it? We're going to take this, slowly ionize to form the carbocation. This is in water, so water will attack, lose a proton, and we make the alcohol. Again, here's our movie. Start off with tert butyl chloride. Slow step. We're just going to break this bond by itself. That's our transition state. There's the carbocation. The nucleophile can now attack from the top or the bottom. We get the protonated alcohol, which quickly loses a proton to give our final product. Any questions? All right, so we said that with primary alkyl halides, we have an SN2 mechanism. With tertiary alkyl halides, we have this SN1 mechanism. Why is that? Well, let's just review very quickly why it is, and it has to do, of course, with carbocation stability. This is a rendition of a carbocation. Secondary carbocation is our positive center. Remember, it's planar. And we have this empty orbital above and below. This is why the nucleophile can come in this way or that way. Nice big empty orbital to put stuff into. With carbocations, remember, we said, well, again, they're nice, happy sp squared, but we said that there was an ordering. The tertiary carbocations were the most stable, secondary, then primary, and then methyl. So why do we only see SN2 reactions with these guys? Well, because they can't form stable carbocations. With secondary or tertiary, yes, you can form a carbocation that's fairly stable. So clearly this is going to be SN1. This is, well, can be anything. And these guys will clearly be SN2. Any questions? The electrostatic potential maps, we've seen these before. Again, for a tertiary, we have just a little bit of positive charge here. And down here for a primary, we have a big honkin' positive charge. Therefore, those are much less stable than a tertiary. Now remember we said that tertiary was stable, but the most stable carbocation is always going to be one that was resonance stabilized. Our favorite thing here, as always, is going to be our benzyl group. Remember the benzyl carbocation. We can move electrons from the ring and delocalize the charge on the ring carbons. The conclusion is that we have positive density on the CH2 and on each of these ring carbons. We do this one more time, we're back where we started. As a rule, any resonance stabilized carbocation is going to be more stable than a tertiary. Any questions? We've said all these things all semester, and so some of this should be fairly familiar, right? All right, here I'm going to take this compound. I'm going to do a simple SN1 reaction. Go ahead and draw the product for this thing. On the exam, the way this question would be written, it would ask you to first draw the carbocation intermediate, and then show the addition of the nucleophile to the carbocation. We know that this is an SN1 reaction because it says so. Therefore, the slow step is going to be breaking the carbon-bromine bond, and we're going to form the planar carbocation. So the first thing you should do is draw that. Carbocation is then going to react with the nucleophile. This is methoxide. Remember, it can attack from either side because it's planar. Methoxide will simply add, and we wind up with the ether as our product. If this was a chiral center, remember, this is an important question. You wind up with a racemic mixture. Equal concentrations of both enantiomers. Any questions? Let's do this again. Here I have a different alkyl halide. I'm telling you that this undergoes an SN1 reaction. Draw the product of this reaction. Well, we would like to do the same thing that we did in the previous. That is, basically rip off the bromine and put the methoxide there, right? In fact, however, this isn't what is formed. What happens here is, remember, we're going to form this carbocation intermediate. Addition does not occur here. In fact, addition occurs at the tertiary center. So this is what we would predict if we just ripped off the bromine and stuck it on. In fact, however, we wind up with the oxygen bonded to the tertiary center. This occurs because our initially formed carbocation here is secondary. Now, it's a secondary carbocation, that's okay, they live, they're real things, but it's sitting right next to a tertiary carbon, isn't it? This undergoes a rearrangement. So this is the other thing that was unique about SN1 reactions. They can undergo rearrangements. And that's because what happens here is what's called a 1,2 hydride shift. We're going to move this hydrogen with its pair of electrons from the tertiary center to the secondary. There it goes. 1,2 hydride shift. We now have the tertiary carbocation, and that's what methoxide adds to. Now, a hydride shift, this isn't magic. It's actually very simple and very, very logical. I made a little movie here on this next slide to show this. This is a carbocation. This is the secondary carbocation we had previously, right next to the tertiary center. And what happens is we shift the hydride from here to here, again, making the tertiary carbocation. What we're going to do here is simply shift the hydride from this carbon to this one, and it looks just something like this. Now, isn't that just so very nice and simple? Hydrogen with its electrons just simply slides over from one to the other to give us the more stable, in this case, secondary carbocation. So to here with a primary carbocation, slide the hydride over, and now it's secondary. Doesn't that make sense when you look at it that way? Any questions? Yeah.
In the test, do you have to do the both shifts, like the two transition, like this rearrangement?
The rearrangement only happens with SN1
Yeah,
reactions.
but if we
If
gonna
you
write the product.
ever make, when you do, if you're looking for rearrangement, okay, what you want to do is look at your initially formed carbocation. In fact, this is probably the exact wording from the exam. For this reaction, the one we saw on the previous slide, I would ask you to show the initially formed carbocation. That's this one. Then, the most stable carbocation following rearrangement, and that's this one. And then the final product. Let's do this again. Again, I tell you it's an SN1 reaction. Go ahead and write the initially formed carbocation, the most stable carbocation following rearrangement, and the product. our initially formed carbocation is going to be this guy. It's on a secondary carbon here, and it's adjacent to a benzyl carbon. Now remember, benzyl carbon carbocations are resonance stabilized. So this is going to be the most stable carbocation center. When we do this, we're going to have a 1,2 hydride shift. Hydrogen with its electrons is simply going to slide over to here. That's going to put our positive charge here on the benzyl carbon. And this is the most stable carbocation. Once we have the most stable carbocation, all we do is add our nucleophile to it, and that's our product. Yeah?
When we draw the carbocation intermediate on the exam, do we have to show the hydrogen, or with the placement of the positive charge, well, can we assume you'll know?
Well, mostly, well, the way I just worded the question, no, you would not have. If I asked you to show the hydride transfer,
Then we have to show the arrows.
let's look at another one. Go ahead, predict the product for this SN1 reaction. Well, we can do this, can't we? We can draw the initially formed carbocation. Bromine's going to leave. That's our slow step. And we're going to have a carbocation right here. Now, imagine yourself this molecule. You're sitting here, you're a secondary carbocation, but you're next to a quaternary carbon, aren't you? All these things bonded to it. You know darn well that things would be much better off if the positive charge was over here. Now, if this was a hydrogen, no problem, right? Because we just slide the hydride over. But here we can't slide a hydride because we don't have a hydrogen. What we do instead is going to grab this entire methyl group and let it slide over from here to here. Exactly like we did the hydride, except the carbon is the thing that slides from here to here. This is a 1,2 methyl shift. Again, the whole methyl group with its electrons are going to slide over. And suddenly we have now a more stable tertiary carbocation. It's exactly like the hydride shift, except it's a methyl. In general, when you have O reactions involving carbocation intermediates, you can rearrange your carbon skeleton lots and lots of times in really wonderful and interesting ways. This is just an example of a very simple shift. Again, you can do very complex rearrangements depending on, what's around here in the nucleophile. But here we've gone from a secondary to a tertiary carbocation. That's good. Nucleophile adds, and we get our product. Any questions? All right, let's sit back and very comfortably say to ourselves, gee, I know this. This is simple. If you have an SN2 reaction, all you have to do is rip off the leaving group, substitute the nucleophile, and invert the configuration. That's all you have to remember. This is going to happen with primary and sometimes secondary centers. If you have an SN1, remember, you lose the leaving group first, rearrange it, add your nucleophile, and remember, if you had stereochemistry, it all goes away. This is the classic SN2, nucleophile, leaving group, electrophile, and there's a substitution product. Let's just go ahead and do a couple quick problems. Predict the products for these SN2 substitution reactions. Now I will do this for you on the exam. If I want you to do SN2, read the words. If I want you to do SN1, I will tell you that too. So go ahead and draw the products for all of these SN2 reactions. Our first one here, our nucleophile is simply methoxide. Our leaving group is going to be bromide. This is going to attack there, and we simply make the ether. This is phenoxide, benzene ring with an O- attached. This behaves just like any other alkoxide. This is our nucleophile. Again, bromine is the leaving group. There's our ether. And finally, the carboxylate anion is our nucleophile. The oxygen attacks, bromine leaves, and that would be our product. SN2 reaction. Substitute leaving group for nucleophile. Leaving group, nucleophile, leaving group, and nucleophile. Can't get much simpler than that. No, it can't get much simpler, but it can get much more complicated. I said on the exam I would tell you if I wanted you to do SN1 or SN2. We wouldn't be very good chemists if we couldn't exert some control over that, right? Turns out that we can. What we're going to talk about are things that tend to affect whether you have SN1 or SN2. This is not going to be a major focus on the exam, but there are a couple important points that you're going to have to remember out of it. So let's just look at that. How do you control whether it's going to be SN1 or SN2? Basically, we're going to look at the substrate. This is the electrophile. You, by choosing your electrophile, you can basically control SN1 or SN2. The nucleophile, we'll see that nucleophile effects, leaving group effects, and most importantly here, the solvent is going to have a big difference. Let's start off with the substrate. We know that in an SN2 reaction, we have to be able to get to the carbon to form this transition state. Because of that, the more junk you have around the carbon, the worse it's going to be at doing SN2 chemistry. Remember, these guys would do SN2, these guys would do SN1. This is mostly to do with the size. If we simply compare bromomethane versus tert-butyl bromide, we have 3 methyl groups here versus 3 hydrogens. If we do an SN2 reaction here, well, let's start with this one then. If we do this guy, our nucleophile has to somehow work its way into all these methyl groups before it can attack this carbon, and that's difficult. Over here, only hydrogens in the way, no steric crowding. That's why primary is so much better than tertiary. Of course, we can model this. This is our tert-butyl bromide. Here's the target right there. Real tough to get to. Here's the target here. Much, much easier. Transition states. Here's our backside attack transition state. Both of these look fairly similar, don't they? However, if we look at the distribution, from this one you should be able to see that because the methyl groups are big, the bromines are further apart. If they're further apart, that means we're going to have charge distribution. Basically, our distance here is about 2.94 angstroms. Down here, we're about 2.5 or so. This additional 0.4 angstroms makes a big, big difference. If we do charges, we can see we have lots of positive charge here in the middle. Here we have much, much less. And we can actually measure those charges. The incoming and leaving groups are about minus 0.88, and here we're about minus 0.7. So there's a big difference in stability, and that's mostly to do with the clutter that's on your central carbon. So tertiary is very bad because it's big. Primary is very good because it's small. It's easy to get at the target. Any questions? We also said we could control whether we get a product based on the nucleophile. Nucleophile effects are predictable. The least reactive in an SN2 is going to be a very poor nucleophile. As we get more and more charge localized, we get a much better reactivity towards SN2. I've correlated this with pKa. pKa of acetic acid is about 4.75. Phenol is a stronger base. It's about almost 10. Hydroxide and water, minus 174 and about 16. Alkoxides tend to be around 16 or so. So bottom line, the stronger the base, the more likely it will be SN2. There's also a periodicity effect. If you simply look at your halogens over here, as you go down the group, these become much, much better at SN2 reactions. Iodide is much, much better, and fluoride is really rotten. The reason for this has to do with polarizability. Down here in the periodic table, you've got big, squishy electron cloud, and it can deform itself, polarize itself, and in doing so, becomes a much better nucleophilic center. So the things that we know about nucleophile, if we want to look at our periodic table, more polarizability is better. If we're just looking at simple alkoxides or something, the stronger the base, the better off. I said we could do leaving groups. The most reactive leaving group. Also, this would be the most reactive nucleophile, wouldn't it? So these guys, down here we have strong bases. These are very weak bases. A weak base is very reactive. A strong base, good nucleophile, but lousy as a leaving group. When I say bases, this guy down here, this is tosylate anion. This is benzene or toluene sulfonic acid. This is what it looks like. Called para-toluene sulfonic acid. You'll learn about that in chapter 13 or 14. But this is a very strong acid. Look at it as an organic equivalent of sulfuric acid. pKa of about -5 to give the sulfonate anion. This is a very classical leaving group. If you want a really, really good SN2 reaction, you will make the tosylate, that's this guy, as your leaving group. Iodide's pretty good, but tosylate is certainly the best. Compare that with methanol. Again, the pKa is -5 here. If we have a very weak base, we have a good leaving group. Here's a strong base. It's a lousy leaving group. Another example, if we have methoxide as a leaving group, lousy, tosylate as a leaving group, very, very good. Quite often, if you read the book and stuff like that, whenever you're doing substitution reactions, first step is going to be to convert whatever it is here into a tosylate. Very, very good. Very, very good leaving group. All right. Probably the one thing that I really want you to remember, aside from maybe this generality, tosylate is better than methoxide, is the solvent effect. Think about it. You're trying to make these things choose the bimolecular reaction as opposed to the carbocation reaction, right? In order to form a carbocation, what do you have to do? You have to rip this sucker off and leave a positive charge. Well, charges are most stable in polar solvents, aren't they? So if you want an SN2 reaction, you don't want carbocations. Therefore, polar solvents are really bad. For an SN2 reaction, you want a non-polar solvent. Now we can even go further than that. Some of you may have heard of like DMSO, DMSO, dimethyl sulfoxide. These are referred to as magic solvents. These are more properly polar aprotic solvents. So they are polar. They will dissolve things very well, but they will not support ionization. So something like DMSO is virtually magic when it comes to SN2 reactions. DMSO really is, like I said, some of you may have heard of it. Dimethyl sulfoxide is a very, very, very good solvent. If you get dimethyl sulfoxide on your skin, it will just go straight in, just like that. And it carries anything that's dissolved in it along with it. This was used, still is used to some extent, to deliver medication, say, to a sore knee. You take it, dissolve it in DMSO, stick it on your knee, it goes straight in, right to the spot. The problem with using DMSO for anything like that is that it's too good, so you have to make sure that you're not sucking in stuff that you don't want to. And also, in the body, dimethyl sulfoxide is reduced to dimethyl sulfide. Dimethyl sulfide is perhaps the most foul-smelling stuff you can ever imagine. So you get DMSO on your hand or your knee, and I can assure you for the next week, nobody's going to want to talk to you. It just sits there and just comes out and out and out, and oh, terrible, terrible stuff. But very good at promoting SN2 reactions. This is DMSO. Again, this is what we reduce off. It's very much a magic solvent for SN2. If you see a reaction, and I don't tell you SN2, but I do say DMSO, think SN2. All right. If you want SN2, unhindered substrate, primary is best, strong nucleophile, strong acid, low pKa leaving group, and nonpolar or polar aprotic solvent. If you want an SN1 reaction, you just want the opposite. You want a hindered substrate, because that'll form a carbocation. You want a weak nucleophile, and you want a polar solvent that's going to ionize this thing. So really, this is how you can control it. Polar solvent, nonpolar solvent, SN1, SN2. Those are the main things to remember. All right. Well, we've made it through substitution. We should all feel good. Unfortunately, just when you thought it was safe, well, it's not. If we take our tert butyl bromide here, and we set it up to do an SN1 reaction, we don't just wind up with a product here that we expect, but we also wind up with an alkene. That is, we have done elimination. What's happening here? We are doing our SN1 chemistry. So in our first step, we're going to lose our halogen. Oh, okay, I guess I'm doing E2 first. I'm sorry, I forgot. So what is happening here? We could do a standard SN1, lose the halogen, and make the carbocation, right? However, imagine yourself methoxide in this molecule floating around. We know that the bromine popping off is going to be slow, isn't it? So what does our base see here, mostly? It sees this huge cloud of hydrogens on the outside. In order to make the alkene, all that has to happen is methoxide has to simply remove one of these hydrogens. When it does, the electrons move in. Now the bromine can leave, and presto, we have our alkene. This reaction is going to happen at the same time, concurrently with the SN1 reaction that we wanted to happen. Now, you know, this is bad, and it's also good, because alkenes are very versatile functional groups. We know lots of reactions, lots of things we can do with them. So elimination reactions are now going to allow us to make alkenes. This reaction that we just showed here, in the rate-limiting transition state, we have our base, we have our alkyl bromide. That's two molecules, isn't it? So this is a bimolecular transition state. It's elimination, so we're going to call it E2. Elimination, second order, or elimination bimolecular. The E2 elimination requires that we pull a hydrogen off at the same time we break the bond to our leaving group. Now, we could do this two ways. We're going to pull off this hydrogen. We can pull it off from the same face or from an opposite face. We'll see in a little bit if we want to do an elimination reaction. The magic base you want to use isn't methoxide. That could be a nice nucleophile. It's this stuff, tert butoxide. I remember we said big was bad. Well, if you want to do substitution, big is bad, right? Here we want this to act as a base, not as a nucleophile. So putting all the methyl groups, still have the O minus. In this case, we would get the alkene. Not just the alkene, but with this particular reaction, we always get the cis alkene. That is, both methyls on the same side. Now, this is going to answer the question of exactly how this reaction occurs. Let's go ahead and consider this two ways. This is our sawhorse configuration of our reactive material. What I'm going to do is take and rotate this a little bit so that the hydrogen is down. Let's put it back. Remember, it's up. I'm going to move this so the hydrogen is now down. That's going to put phenyl group over here, methyl up, and it looks like that. If now methoxide comes in and removes this hydrogen, electrons will flow in, this will go up, and we would get this as our product. Once again, two methyl groups are on the same side here, and are on the same side in our product. This is referred to as a trans-elimination. And all that means is the hydrogen and the group that leaves are opposite each other. Opposite means anti, or more properly, anterofacial. Opposite sides of the face. Once again, these guys must be in the same plane. There's where anterofacial comes in. This is the hydrogen that's removed. That's the bromine that goes. Let's do this the opposite way. If we had, this is the same thing we started with, I'm going to now take it and rotate it the other way so the hydrogen is pointing up. When I do that, the phenyl's going to come down, methyl's going to come over, and I would get this. If we had this hydrogen pulled off when this bromine left, This would be a cis elimination, but we would get the trans product. Methyl groups are on opposite faces, trans. The fact is that we get only the cis product, therefore, an E2 elimination is a trans elimination. A hydrogen and a leaving group must be in the same plane, but on opposite sides. Let's, of course, watch the movie. Here we have just a simple alkyl halide. We're going to pull the hydrogen off. This is going to be our leaving group. The strong base comes in, pulls off the hydrogen. As it does, the electrons move in to form the double bond, and the leaving group leaves. Both things are in the transition state, so it's concerted, and we wind up with our alkene. Again, it's a trans elimination. There's actually beauty to it. You want to watch it again. This comes off, electrons go in, this leaves, all at the same time. Now, like I said, this is a concerted reaction, just like the SN2 was concerted. So we have only a transition state. We have no intermediate. Any questions? Well, let's go ahead and do an E2 elimination here. Go ahead and predict the product from this elimination reaction. We are looking for the hydrogen that we pull off and the halogen to be in the same plane. Remember, this is pulled off, this leaves at the same time. Going to lose this hydrogen, this bromine, and we make this alkene. Now that was simple. But there's always a but, isn't there? Think about it. I've set this up for you, haven't I? I've shown the hydrogen here. There's a hydrogen over here too, isn't there? There is. Why in the world did we pull this one instead of this one? What would happen if we pulled the other one? The other product, we're going to yank the hydrogen off here. The electrons would move in. Bromine would still leave. They're still planar, aren't they? They're still antirofacial. But this is the alkene we would get. Now the fact is, this is what you really get. This you don't get so much of. Why is that? Well, because some Russian chemist some time ago noticed it, just like Markovnikov did his thing. This guy is named Zaitsev. This is Zaitsev's rule. Basically, Zaitsev's rule says that the most highly substituted alkene is going to be the one formed. Look at this alkene. We have 3 carbons attached to it. Down here, we have 2 carbons. This is more highly substituted. Zaitsev says this is our major product. And he's right. So you always want to go to a situation where you're going to form the most highly substituted alkene. Zaitsev's rule. All right, so if you do an E2 elimination, what do you have to know? Exam's coming up. What do you have to know? E2 elimination. Going to be concerted, isn't it? The hydrogen that's removed must be anti and coplanar with the leaving group and interfacial. It's a trans elimination. If we have a choice of products, always choose the most highly substituted alkene. Well, that's all you have to know. Now, we can also do our reaction here, get the same product, but the kinetics are different. Instead of a bimolecular, we can set this thing up so it actually is unimolecular. So it's equivalent to an SN1 reaction. What's happening here, if we put this in a polar solvent, what we see is an E1 reaction. Again, elimination, but now first order. Now we know all this already from SN1. What's going to happen? We're going to start off with our alkyl halide. Step 1, in our slow step, we're going to form a carbocation. Step 2, once we make the carbocation, instead of the nucleophile attacking, we're going to simply yank off a hydrogen to make the alkene. Just like you learned for SN1, anytime there's a carbocation, you can rearrange. So E1 and SN1 are very, very similar. Polar solvent makes it work. And again, you can get rearrangements. Just like in the SN1, we have a transition state, the carbocation intermediate. Only one thing in the transition state, that's why it is unimolecular. Let's look at one more movie. Here we have our tert-butyl chloride. What's going to happen is chlorine's going to leave, give the carbocation. Now we're going to yank off the hydrogen to give our alkene. This looks a whole lot like the standard SN1 reaction, except once we make the carbocation, we pull off one of these hydrogens. Here's our slow step. And there's our carbocation. Once we're at this point, instead of attacking, we simply yank off a hydrogen and make the alkene. All right, now it's getting a little messy, isn't it? Because we can have substitution or elimination. Let's talk just a little bit about how you control which one you get. This is the thing to remember. If you want elimination to occur as opposed to substitution, you want a big honkin' base. Whenever on the exam you see tert-butoxide, that's going to tell you it's an elimination reaction. Okay? That's simple to remember. Write it on your hand. Terp-butoxide means elimination. If it's little, you can do substitution. If it's big, it's elimination. Here's just an example of what we just said. Here, methoxide can attack virtually 100% yield. If we have terp-butoxide, instead of attacking here, what happens is we are prone to pull off the hydrogen and get the alkene. Again, this is virtually 100%. So the thing to remember is the little tiny base is good for getting in and reacting. This is terp-butoxide. It's big, can't quite fit in there. It only acts as a base. Strong base, really hindered, promotes E2. Now that's the real key thing to remember. Here's the full set. If we're going to do an SN2 reaction, we talked about these. We want a primary as opposed to tertiary. We want a good nucleophile, low pKa leaving group, tosylate or iodide is good. And we want nonpolar or polar acrylic. If we want E2 elimination, all you have to remember is terp-butoxide. That will give you E2 because it can't get in there. SN1 and E1, well, that's just a real toss-up because they're both going to form stable carbocations. They both happen in polar solvents. You almost always get a mixture of products. So let's see what this looks like on the exam. First thing you notice, these are all terp-butoxide and butanol. What do you say to yourself? I'm doing elimination. It's going to be a simple E2 elimination. So draw the alkenes for all these guys. Our first one here, we say, okay, this is a simple E2 elimination. We're going to pull the hydrogen off an adjacent carbon. That's this one. Bromine's going to leave. We know that these must be trans to each other and tetrafacial. But here it doesn't matter because we have two hydrogens. We're going to pull this off. Our product is simply going to be styrene. Leaving group leaves, go to the hydrogen, and make a double bond. Here, instead of a halogen, I put a tosylate just to show that I can. Remember, tosylate's a very good leaving group. But we're in terp-butoxide butanol, we're going to get a simple E2 elimination. That means butoxide is going to pull a hydrogen off of one of these guys, tosylate is going to leave, and we simply make the alkene. Now finally, let's look at this guy. This is a good test question. We're going to do an E2 elimination, aren't we? We know that we must pull off a hydrogen that is trans to the leaving group, right? So let's look at our leaving group here. It's equatorial, right? The hydrogen here is axial. Are those two trans? No, they're cis, aren't they? So you can't pull this hydrogen off, can you? If this is equatorial, the only trans hydrogen is this guy that's also equatorial. Therefore, instead of the most highly substituted alkene, this is the one that we would form. Now we'll look at this a little more closely. Remember, in order to do the elimination here, the hydrogen has to be up, the bromine has to be down. So they both have to be axial. So let's start off with this stuff. We're going to do a ring inversion so that the bromine and this hydrogen are both axial. In this view, you can clearly see that this bromine is antifacial to the methyl group, isn't it? That's not going to work. So the only hydrogen you can pull off is this guy. Because they must be anti and coplanar, terbutoxide will simply pull this hydrogen off, and we wind up with this alkene. Any questions? This, I will be honest with you, is a very classic exam question. Make sure you understand why you get the non-Sate-Seth, the anti-Sate-Seth product, simply because the methyl group and the bromine are trans here. Has to be a hydrogen, and so this is what happens. Let's do one more simple reaction. Again, a good exam question. We're starting with cyclohexene. I want you to make 1,3-cyclohexadiene. Suggest a synthesis. It's a fitting problem for the last slide in organic one. Well, whenever you do a synthesis, what do? You talk to yourself. You say, what kind of compound is it? It's an alkene I'm trying to make a double bond, aren't I? How do I know to make double bonds? By an elimination reaction. All right, we can do this. That means that at this carbon with the little arrow, we had a leaving group. We pulled a hydrogen off from here, leaving group left, and we made a double bond, right? We know that. How are you going to put a leaving group here? Instantly, of course, you're thinking back to chapter 10, aren't you? This is an alkene, isn't it? It has, okay, well, we know that we're going to use terbutoxide and butanol, but we need something with a leaving group here. We know that bromine would be a fine leaving group. But do we know any simple way to put a bromine just on this ring at that position? Ask yourself, what is magic about this position? It's adjacent to a double bond, isn't it? Remember the magic word we used? Allylic? It is an allylic position. How do you make allylic halides? The allylic bromide is done by a free radical bromination. Remember? Because the radical you form is stable. How do we make the allylic radical? Something simple like N-bromosuccinimide. Shine a light on it. Carbon 10 is simply our solvent. So step one, we do an allylic bromination to get the bromide. Step two, we want to do an E2 elimination. So we use hurt butoxide. That's going to push it to E2, isn't it? And presto, we have our product. Any questions? Well, again, we have survived 234, haven't we? Once again, on Thursday, we don't have lab anymore. We're done with that. Please make sure you get all your lab things in. On Thursday, we will do the sample exam for E3. I will put the sample exam up on Blackboard, and I might even email one to you, depending on my mood. Okay? Work that, bring it to class, and let's go over it.